What if I told you there is a liquid that can boil and freeze at the very same time? It sounds like something straight out of a science fiction movie, right? But this isn't Hollywood magic. It's a real mind-bending phenomenon that happens right here on Earth. Stick around, because we're about to dive into one of the weirdest, most fascinating concepts in all of physics. This incredible state is known as the triple point. It's a specific razor-sharp condition of temperature and pressure where a substance can exist as a solid, a liquid, and a gas, all at once, in perfect balance. Imagine a container where you can see ice forming, water sloshing around, and water vapor bubbling up, all in a stable, harmonious dance. That's the triple point. It's not a chaotic mess, but a state of thermodynamic equilibrium. Each phase solid, liquid, gas is converting into the other two at exactly the same rate. So ice is sublimating into vapor just as fast as vapor is depositing into ice, and liquid is freezing just as fast as ice is melting. It's a perfect three-way balancing act. This isn't just a party trick for scientists. It's a fundamental property of matter that has some surprisingly practical applications. Let's start with a substance we all know and love: water. You might think water freezes at 0 degrees Celsius and boils at 100 degrees, but that's just at our everyday atmospheric pressure. The triple point of water is a bit different. It occurs at a very precise temperature of 0.01 degrees Celsius, just a tiny fraction above the normal freezing point, and a very, very low pressure of about 611.657 pascals. For perspective, the atmospheric pressure we experience at sea level is over 101,000 pascals. So, you need to create a near-perfect vacuum to witness this. Because this triple point is so specific and repeatable, it's become a cornerstone of modern science. How do we know that a thermometer is accurate? We calibrate it using a fixed known point. And what could be more fixed than a fundamental property of water itself? Laboratories around the world use what are called triple point cells. These are sealed glass vessels containing pure air-free water. When they're properly prepared, they can maintain water at its triple point for a long time. Scientists then insert a thermometer into the cell to calibrate it against this incredibly stable temperature. In fact, the triple point of water is so fundamental that it's used to define the Kelvin, the official SI-based unit of thermodynamic temperature. 1 Kelvin is defined as 1/273.16 of the thermodynamic temperature of the triple point of water. So every time you see a temperature reading, you can thank the strange three-phase dance of water for its accuracy. But water isn't the only substance with this quirky property. Let's talk about another common chemical, carbon dioxide. We usually encounter CO2 as a gas we exhale, but under pressure, it can be a solid known as dry ice. The triple point of carbon dioxide happens at a chilly -56.6 degrees Celsius and a pressure of about 5.1 times our normal atmospheric pressure. This is a crucial data point for anyone working with CO2. If you've ever seen dry ice, you'll notice it doesn't melt into a liquid puddle. Instead, it goes straight from a solid to a gas in a process called sublimation. For scientists, particularly physicists and chemists, the triple point is more than just a curiosity or a calibration tool. It's a gateway to understanding the very nature of matter. It represents a critical point on what's called a phase diagram, which is basically a map that shows what state a substance will be in at any given temperature and pressure. The lines on this map represent the boundaries where phase transitions happen: melting, boiling, freezing, and so on. The triple point is the unique location where all three of these boundary lines meet. Studying what happens at and around the triple point allows researchers to test and refine their theories about phase transitions. It's a key concept in thermodynamics, the branch of physics that deals with heat, work, and energy. By observing how substances behave under these extreme, precise conditions, scientists can build more accurate models of molecular interactions. These models are crucial for developing new materials, improving industrial processes, and even understanding geological phenomena deep within the Earth or on other planets, where temperatures and pressures are far what we experience on the surface. One of the most striking things about the triple point is its fragility. It's not just rare, it's unbelievably precise. The equilibrium is a delicate balancing act. If you change the pressure or temperature even slightly, the balance is broken and the substance will collapse into just one or two phases. For instance, if you take a container of water at its triple point and increase the pressure just a tiny bit, all the vapor will condense and you'll be left with only liquid and solid. If you increase the temperature, the ice will melt and you'll have liquid and vapor. It's this extreme sensitivity that makes it such a perfect reference standard. It's a non-negotiable point defined by the laws of physics, a true constant of nature that we can rely on. Now, things get even weirder. While we've been talking about the triple point, some substances are so complex that they can have multiple triple points. A great example of this is sulfur. Sulfur is what's known as a polymorphic substance, meaning its solid form can exist in different crystal structures. At different pressures and temperatures, sulfur atoms can arrange themselves into either a rhombic or a monoclinic crystal lattice. Each of these solid forms has its own set of properties, and as a result, sulfur has not one, not two, but at least three known triple points on its phase diagram. There's a point where rhombic solid, monoclinic solid, and liquid sulfur coexist. There's another where monoclinic solid, liquid, and vapor coexist. And a third where rhombic solid, liquid, and vapor coexist, though this one is metastable, meaning it's not truly stable. This complexity shows just how intricate the world of material science can be. The applications of triple points extend far beyond calibrating thermometers. They play a vital role in cutting-edge fields like cryogenics, the science of producing and behaving of materials at very low temperatures. Gases like argon, neon, and oxygen all have their own unique triple points at very low temperatures. These points are used as fixed temperature references for calibrating equipment used in research that requires extreme cold, such as in particle accelerators, or for creating superconducting magnets. In space research, understanding the triple points of substances like methane or nitrogen is critical. These substances are found on planets like Mars or moons like Titan, and their phase behavior under different planetary conditions dictates the weather, geology, and potential for finding environments that could, even hypothetically, support life. The phase diagram of methane, for example, helps scientists interpret data from probes and rovers, telling them whether they're looking at methane ice, liquid methane rivers, or a methane atmosphere. Ultimately, the triple point is more than just a scientific fact. It's a cornerstone of how we measure and understand our physical world. The International Temperature Scale of 1990, or ITS 90, is the official scale used by standards organizations worldwide. It's not defined by just one or 2 points, but by a series of fixed points based on the phase transitions of various pure substances. These include the triple points of hydrogen, neon, oxygen, argon, mercury, and of course, water. These points are the rungs on the ladder of temperature measurement, allowing scientists everywhere to speak the same language and ensure their results are comparable and accurate. The triple point helps anchor our entire system of measurement, providing a solid, reproducible foundation based on the fundamental laws of nature. So, when you think about it, the triple point is a beautiful and rare moment of perfect symmetry in the universe. In our everyday lives, we're used to seeing solid, liquid, and gas as distinct separate states. Water is either ice, liquid, or steam. But nature has these hidden little corners, these precise, fleeting moments where the rules seem to bend, and all three states can come together in a delicate truce. It's a powerful reminder that the universe is full of wonders that defy our everyday intuition. The laws of physics allow for these incredible phenomena, pushing the boundaries of what we think is possible. From a seemingly simple observation, a liquid that boils and freezes simultaneously, we've uncovered a concept that defines our temperature scale, enables advanced technology, and helps us explore other worlds. The triple point is a perfect example of how science can be far stranger and far more elegant than fiction. It proves that by asking what if and looking closely at the world around us, we can discover truths that are both profoundly weird and incredibly useful. Thanks for joining me on this deep dive into the triple point. What other bizarre scientific facts do you think we should explore next? Let me know in the comments below. If you enjoyed this journey into the weird world of physics, don't forget to like this video, subscribe to the channel, and hit that notification bell so you don't miss our next adventure. See you next time.